Behind every stronger project is a team with a one vision. Hello everyone, I'm Dalal and I keep everything organized and attention to the details.
I am Manar and I turn ideas into clear analysis and particle direction.
I am Noor Alajmi and I help keep the team balanced and focused.
I am Noor Jassim and I make sure the details stay organized and complete.
I'm Shaikha and I'll be guiding you through our project today, ensuring that we keep the technical details clear and easy to follow. Now let's dive into our work on salt entrainer systems for the dehydration of bioethanol. Bioethanol is one of the most widely used renewable fuels, primarily produced through biomass fermentation. This is followed by distillation, where ethanol is separated from water to increase its purity. However, this process is limited by the ethanol-water azeotrope, which makes complete separation challenging. But here lies the real challenge. Ethanol and water interact strongly through hydrogen bonding. At a specific composition, they form what is known as a minimum boiling azeotrope. At this point, the vapor and liquid phases have identical compositions. As a result, conventional distillation can no longer increase the purity beyond this limit. This limits ethanol purity to about 95.6%, which means an additional separation method is needed. At this stage, several separation methods can be considered, starting with simple distillation, which is limited due to the azeotrope. Next, we have pressure swing distillation that changes operating conditions but increases the complexity, while azeotropic distillation introduces additional chemicals, and membrane-based methods can be effective but are often costly, whereas dividing wall columns improve the efficiency but require advanced design. And finally, extractive distillation, which enhances separation by modifying relative volatility. Among these options, extractive distillation stands out as the most suitable approach for our system, and this is where our solution begins. To overcome this limitation, an entrainer is introduced to alter the separation behavior. Entrainers can be classified into three main categories: organic salts, inorganic salts, and ionic liquids. Each offers different advantages in terms of efficiency, cost, and environmental considerations. In this study, we focus on inorganic salts due to their strong affinity with water and their ability to effectively break the azeotropic behavior. After identifying inorganic salts as the most suitable entrainer category, the next step was to evaluate each salt individually and examine its effect on separation performance. The first salt considered was lithium chloride, or LiCl. Lithium chloride shows a strong salting out effect due to its strong interaction with water molecules. This reduces water volatility and improves ethanol separation. From the y-axis diagrams, the equilibrium curve shifts clearly away from the diagonal line, indicating good separation performance. The next salt considered was sodium chloride, or NaCl. Sodium chloride also affects the equilibrium behavior of the system, but its impact is more limited. The y-axis diagrams show a small deviation from the diagonal line, which means the improvement in separation remains modest. In addition, higher concentrations may lead to precipitation inside the system. And the third salt considered was potassium chloride, or CaCl. Potassium chloride provides a moderate salting out effect and improves separation more so than NaCl. This can be seen from the larger shift in the y-axis diagrams, where the vapor phase becomes richer in ethanol. However, the effect is still moderate, and precipitation may also occur at higher concentrations. And the final salt considered was calcium chloride, or CaCl₂. Calcium chloride is highly soluble in water and interacts strongly with water molecules in the liquid phase. This gives a more noticeable effect on the vapor-liquid equilibrium and improves the separation behavior. As the entrainer concentration increases, the y-axis diagrams show a clearer shift away from the diagonal line, indicating stronger ethanol enrichment in the vapor phase. These results show that each salt affects the equilibrium behavior differently, leading to different levels of separation improvement. To analyze the effect of these salts, a simulation approach was applied using Aspen Plus. The ethanol water system with salts was modeled using the electrolyte E-NRTL model to accurately represent vapor-liquid equilibrium behavior. The process was simulated under steady-state conditions using a distillation column with 17 stages. The feed was introduced at stage 11, while the salt was added at stage 5. The system was operated at an atmospheric pressure with a feed temperature of approximately 78 degrees Celsius. The performance was evaluated based on ethanol purity and reboiler duty. Based on the previous analysis, the technical feasibility and main constraints of each salt can now be summarized. Lithium chloride shows the strongest technical performance, supported by high solubility and strong interaction with water. However, it requires careful concentration control to avoid scaling or precipitation. Sodium chloride offers a moderate improvement in separation, but its overall effect remains limited, with a possible risk of precipitation. Potassium chloride is stable and shows a salting out effect, but its separation performance is relatively weak compared to the other salts. And calcium chloride provides strong separation with good feasibility, although corrosion and precipitation must be considered during operation. Overall, lithium chloride and calcium chloride show the strongest technical potential, while sodium chloride and potassium chloride remain less effective. However, selecting the most suitable option requires considering not only technical feasibility and operational constraints, but also economic and environmental factors. After evaluating the technical performance, the economic and environmental aspects were also considered for each salt. Sodium chloride is the most economical option with low cost and low toxicity, making it favorable from both economic and environmental perspectives. Potassium chloride and calcium chloride show intermediate cost levels, with acceptable energy requirements and low toxicity, providing a balanced performance. In contrast, lithium chloride has a significantly higher cost and higher toxicity, despite its strong separation performance. Therefore, although lithium chloride performs best technically, its economic and environmental limitations reduce its overall suitability. This comparison highlights the importance of balancing performance with cost and sustainability when selecting the most appropriate entrainer. Based on the combined technical, economic, and environmental evaluation, calcium chloride was selected as the final entrainer. Calcium chloride provides strong separation performance while maintaining moderate energy requirements. It's also cost-effective, widely available, and easier to handle compared to other options. In addition, it has lower toxicity, making it more suitable from an environmental perspective. Therefore, calcium chloride represents the most balanced and practical choice for this process. This block flow diagram shows the overall process using calcium chloride as the selected entrainer. The ethanol water feed enters the distillation column, while the salt is added separately to enhance the separation. High purity ethanol leaves from the top of the column, while the bottom stream containing water and salt is sent to a flash drum. There, water is removed and the salt is recovered and recycled back into the process. This project highlighted the challenge of ethanol dehydration and the importance of selecting an effective separation approach. Through simulation and evaluation, we showed how engineering analysis can support a more efficient and practical bioethanol purification process. Thank you for watching.